lecture of this afternoon, which will be given by Rolf. Rolf has a background in organic chemistry. He has over 20 years of experience in chemical technologies to convert green feedstocks such as vegetable oil, carbohydrates into all kinds of chemical products, including coatings, paints, and bio-based materials. And Rolf leads the polymer synthesis work package of the Champion project. So Rolf, the floor is yours.
Thank you, Dan, for your kind introduction. Welcome, everybody. Today I will give a presentation about promising bio-based resins for coatings and adhesives, safer, more sustainable, and circular. This is a brief outline of my presentation. First, I will be setting the scene, sketching a background, talking about conversion of a linear to a more circular economy. Then I will zoom in a bit on the differences between thermoplastic materials versus thermoset materials. And then I will mention two big disadvantages of current thermosets and how we would like to address that in the Champion project. I will introduce the project briefly and its objectives. Then I will zoom in on the type of chemistry that we use in that project, which is aza-Michael chemistry. And then I will summarize a few of the intermediate results that we have obtained so far, and we'll close with an outlook with plans on what we're going to do in the remaining part of the project. And my final screen will be two take-home messages. So first, setting the scene a bit. Currently, basically, we have a linear economy, and this certainly goes for the materials that we produce. So we take feedstock, we produce our plastic materials, for instance, and then most of it is either landfilled. So this is globally. In certain parts of the world, these numbers are different. But globally, about 40% of our plastics are landfilled. About a third is leaked into the environment, and about 14% is incinerated to recover energy. And only 14% is collected for recycling. And of that 14%, finally, only 2% is really used in closed loop recycling, meaning that it is reused again in an application that is of similar value as its original application. So we would like to change that, significantly reduce the amount of feedstock that we use to create our materials. So we would like to integrate already during the design and production a circular by design concept, in which we try to design products that are meant to be recycled after their use. And it is almost inevitable that not all materials can become part of a closed loop cycle. But in case any new virgin material is needed, we would like this to be bio-based. So either using CO2 or using biomass to replenish the material pool. So there are basically two types of plastic, and the overwhelming majority of plastics are so-called thermoplastic materials. These are materials that consist of long linear polymer chains, which can be remelted and reshaped by heating. So this means that thermoplastics have a limited mechanical stability at very high temperatures, but it also means that they are easier to recycle. And they are mainly used in packaging, building, and construction. On the other hand, thermoset materials, these are made from chemicals that are reacted by heating them, and then they will form a cross-linked polymer network, as you can see in the scheme below. These thermoset materials, once set, they cannot be remelted or reshaped. And this is good because it provides them with very high mechanical stability, even at very high temperatures. But it also means that they are very difficult to recycle. And the main applications where thermosets are used are in building and construction, electronics, automotive, and so-called case applications, coatings, adhesives, sealants, and elastomers. If you look at Thermoset chemistry today, you see a few main types of chemistries that are being used. One of them is called epoxy resins. And to the right, you see a schematic depiction of the chemistry that's involved. So for epoxies, you need amines. I will change my mouse to a pointer, 1 second. So you take amines and you react them with compounds that have multiple epoxy groups. And amines and epoxies react to form this polymer chain. In practice, this is a cross-linked network, but only the linear chains are shown for simplicity reasons. A second important class of thermosets are the so-called polyurethanes. In this case, you take a so-called isocyanate and you react it with a polyol and you end up with a polyurethane. And this is the urethane linkage. A third important class of thermoset resins are the formaldehyde resins. And here you have phenol formaldehyde, urea formaldehyde, and melamine formaldehyde. And in this case, you take one building block, which could be phenol, melamine, or urea, and you react it with formaldehyde. And then you form a cross-linked network known as PF, UF, or MF materials. And finally, there's a big class of thermosets called unsaturated polyester resins. In this case, you take a polyester resin with activated double bonds and you react it with a diluent, a reactive diluent. In almost all cases, this is styrene. And then you end up with a strongly cross-linked network. And these materials are used a lot also in composite materials. Most of these thermoset chemistries are non-reversible chemistries, meaning you can't reverse the materials back into monomers. And secondly, and importantly, many of these chemistries use toxic chemicals, for instance, based on bisphenol A, on isocyanates, or by using formaldehyde. And styrene is also hazardous. So we looked at, there's one slide missing. What we did was try to look for alternatives for these isocyanate and epoxy systems. And these are usually mixed together and then they react sometimes already at room temperature. So we were looking at a more friendly chemistry that is also reactive at room temperature, but does not use any isocyanates or epoxies. And we succeeded in that for a very specific application, so-called elastomer embedding resins, in which an isocyanate-based formulation is currently being used, which is mixed on-site and then poured to embed tram rails or train rails in order to get noise reduction and vibration reduction. So we succeeded in finding an alternative chemistry for this particular application, filed a patent, so cannot yet disclose the details of the chemistry, but we think that this chemistry provides many opportunities also in other applications. So to zoom in a bit on the chemistry that we used for this application, this is a so-called Michael addition chemistry. And it is depicted generally here. So in Michael addition chemistry, if you want to make polymers, you need a Michael donor, which is multifunctional. So look at the end groups here. And you need a so-called Michael acceptor, which also has at least 2 reactive groups. And together they react already at room temperature. And they give long cross-linked polymer networks. In this case, for this particular application, the Michael donor was based on a vegetable oil-based polyester polyol, and the Michael acceptor was a non-bio-based moiety. And we found that the polymer properties could be tuned by changing the structure of R1 or R2, or changing the number of Michael donor or Michael acceptor groups, and also by changing the ratio in which the two reactive components are mixed. So now I move to Champion. Champion stands for Circular High Performance aza-Michael polymers as innovative materials originating from nature. And here I show briefly the concept. So we would like to change from a linear use of materials to a more circular use of materials. So during the design of our new system, we take safety into account by screening all the chemicals that we make and subject them to bioassays to test for human toxicity. And we also use circular by design methods. So we think of end-of-life scenarios before designing the various aza-Michael polymer systems. We focus particularly on adhesives, coatings, and home care formulations. And end-of-life scenarios that are being investigated include recycling, digestion, and biodegradation. And biodegradation is particularly relevant for the home care applications in which it is very difficult to recycle after use. Champion is a 3.5-year project under the Horizon 2020 Bio Based Industries program. It will run until November 2023, and the project contains 14 partners coming from 6 different European countries. So we aim to replace conventional polymers with novel bio-based polymers that are more sustainable, safer, and at least equal in performance to benchmark systems. And this includes end-of-life options. So 4 applications are being targeted that I already mentioned. So coatings, and our initial target will be a kitchen counter coating. We also focus on textile coatings and specifically automotive interior coatings. Structural adhesives, so glues for exterior long-term force-bearing applications. And finally, home care products. And our initial target here will be a laundry detergent ingredient. So the project includes sustainability, safer use of materials for industrially relevant applications, and performance is continuously being screened by our end user partners. So what we aim for is at least 1 new bio-based polymer for each of the application areas, and benchmarked against current materials. Here you see the partners. So you see that the whole chain has been represented, starting from the production of bio-based chemicals and synthetic procedures, polymerization, scaling up the materials that are selected for final performance testing, end users testing the technical performance of the materials, and included are toxicity and end-of-life scenarios, and also policy and sustainability. So comparing the classical Michael addition that we've used in the railway elastomer application with the aza-Michael chemistry that we use in Champion, you see that classical Michael addition involves the formation of carbon-carbon bonds. You need a strong base, otherwise the reaction will not proceed. And what you end up, because you make carbon-carbon bonds, which are very difficult to break, you end up with materials that are more difficult to recycle. So classical Michael chemistry is not the focus of Champion. In the case of aza-Michael addition, you form nitrogen carbon bonds, and nitrogen is both a nucleophile in this reaction as well as the catalyst. So no additional base catalyst is required. And in case of the aza-Michael addition, you have the option of reversibility. So going back to your building blocks after its end after its service life. So we have an additional option for recycling here. So some of the results that we have obtained so far, and note that these are preliminary results. We are about halfway in the project. So we intend, let's say, in about half a year or so, to give you an update on the results that we achieve. And maybe then we can also be a bit more specific in the types of chemicals that we use. But so far we have produced several novel bio-based diamines and also several novel bio-based Michael accepting pre-polymers. And these are the two main reactive components of our system. And these are currently being tested in a broad series of curing reactions, screening for the best materials and sending these over to end users for further testing. And initially, we had difficulty in making materials which had sufficient hardness. So basically, most of the materials were relatively soft, but this has recently been improved, and I will come back to that. So here you see these are lab scale experiments. So these are some of the materials that we produce. And these are usually post-cured briefly in an oven to see if any increase in mechanical properties can be obtained. So hardness is a very important property for the applications that we are targeting. And here you see the so-called Shore D or shore hardness scales. You have different shore hardness scales. The very soft materials are so-called Shore OO, very soft materials. Then you have intermediate hardness for Shore A. So these are still relatively soft, but we are aiming for relatively hard materials in the Shore D range. So Shore D values of 50 are an important target in the project. And for the automotive interior coatings, for which you need relatively flexible products, hardness can also be a bit softer than 50D. But for the kitchen tabletop coating and also for the structural adhesives, the 50 Shore D value is a minimum value that we would like to see. So what we found is that we could increase the hardness of the materials that we make by reacting the amount of reactive groups per molecule. And this makes sense because if you have more reactive groups, you can make a more densely cross-linked polymer network. And usually in this way, you end up with harder materials. And this is what we found. So here we have some anonymized results in which the functionality of diamine D2 is higher than the functionality of diamine D1. And here you see 4 different Michael accepting pre-polymers, in which again, functionality of A4 is larger than A3, which is larger than A2, which is larger than A1. And if you use combinations of diamines and Michael accepting pre-polymers that have a relatively low functionality, functional density, then you end up with relatively low values for the shore hardness. And in this case, you also have quite a low cross-link density. But if you go to more functionalized materials, you see that hardness increases, and this corresponds to the cross-link density of your polymer network. Shore D hardness is a very convenient hardness type because there are easy tools to use to measure hardness. So you can be very quick in your screening of materials. A brief outlook on what we on the plans we still have in Champion. First, we're going to scale up from lab scale to several kilogram scale for those diamines and Michael accepting pre-polymers that give the most promising performance in the end use applications. We are going to optimize this performance, of course, in the remainder of the project. And we are also going to evaluate end-of-life options for the aza-Michael materials. So we will look at a a reversibility of the polymerization, the so-called retro aza-Michael reaction. And in this case, in an ideal case, you would get your monomers that you used at the start. You get those back and you can reuse them again. And secondly, and this is also particularly important for home care products, we are going to look at biodegradation. So not only of the coatings, but also of the home care products. So I'd like to close this presentation by 2 take-home messages. We believe firmly that safe by design and circular by design principles should become an integral part of synthetic material development. So not focus only on performance for the end application, but also focus on what happens after its service life. And secondly, I hope to have shown you that bio-based solutions are on the way as alternatives for fossil-derived and sometimes hazardous ingredients for reactive coatings and adhesives. Thank you.